a professor at the particle physics department at the University of Oslo, and also a researcher at CERN in Geneva in Switzerland, and part of the team that, or many thousand people that have worked on finding the Higgs boson that they were so certain about in 4th of July 2012. So they had a conference then, and we'll give a 30-minute talk around that on the Higgs boson, and then we'll have a discussion and take questions at that. I'm a master student at the Art Academy here in Oslo. I'm asked to have a discussion with Alex. So
thank you for the invitation to come here and speak about this favorite subject of mine the last 2 years about. So I've been giving talks like this for more than a year, and we have more and more materials. The talks have been getting longer and longer. But Daniel asked me, first for 20 minutes, and then we changed it to half an hour. So we'll see how it goes. So I wanted to start by saying that the Higgs boson is something about particle physics. So what is particle physics? This is a book, it's in Norwegian, written by a former postdoc in a research group here in Sunset, The Secret Particles. And he takes 60 pages to introduce what they call the standard model of fundamental particles and their interactions. And at the end he asks the question, so how does the universe work? And he answers the question himself. Everything is made of fermions, which is some kind of material, which are held together by bosons. So we want to look into a little bit what this sentence means. But basically particle physics is the study of the smallest, most fundamental particles of nature and how they interact with each other. Well, what do we mean by fundamental? Democritus, 460 years before Christ, he was the first one to introduce the idea that if you took some object and started dividing it up into pieces, the pieces would get smaller and smaller, and you would end up with something which was not divisible. And this, whatever it was, he called atom. Of course, today we have a slightly different interpretation of atom. This is a table of the chemical elements. Each box in this table represents a specific kind of atom. So this looks quite complicated. I think there are more than 110 different kinds of elements, of types of atoms. This is very, very complicated. Is nature really so complicated? The answer is no. It turns out we look inside these atoms, there weren't little points or little triangles or something which you couldn't break apart. The atom could be split. It could be taken into pieces. And what we found out was that there's a kind of cloud of electrons on the outside of the atom, giving it its size. And then deep inside the atom is a nucleus, which for a long time we wondered if it was a kind of a pudding spread throughout. And then Rutherford showed in the beginning of the previous century that the nucleus was some very small, very dense object. And then when we looked even closer, we found out that the nucleus is again composed of smaller things. We wondered if these were indivisible. These are protons with charged electron and neutrons, which are electrically neutral. And if you look even closer at these protons and neutrons, even they are composed of smaller things, quarks. And the quarks are held together by other particles we call gluons. And for the past 50 years, we have not been able to find any structure inside the electron or these quarks. So as far as we know, these are the fundamental building blocks of the universe. We cannot provide them to the best of our knowledge. And it's amazing that this complexity is describable by just a small number of particles and one or two kinds of forces. then we get this amazing complexity of these, get what you see around us. This book, that book, which is this book here, it contains all the important results in particle physics up to July 2008. It's enormous. There are lots of particles. In the 1950s and 1960s, there was an explosion in the number of particles at research laboratories. And we were back to the complicated table of the chemical elements. Are all these particles fundamental? And it turns out the answer is no. But we found some more fundamental things. These quarks, which I talked about, so in the proton and neutron we have U and D quarks, but there are 4 more, which are heavier and unstable. There are these things we call leptons, the most familiar of which is the electron, which we have in us all around us in our atoms to make them neutral. It has heavier cousins, the mu and the tau charged leptons, and then there are some neutrinos, which until 5 years ago we thought were completely massless. Now we know they also have mass, but they're very, very tiny. On the right, we have some other particles. Up here it says forces. These are also fundamental particles, but these particles are the things which mediate fundamental forces that we know about, at least 3 of the 4. We know about electromagnetism. We know about the weak force, which is responsible for radioactivity and the burning of hydrogen to helium in the sun. We know about the strong force, which keeps the neutron and proton together and then leaks out a little bit, and then we make stable nuclei. But then there's this cloud. Here, what is this cloud? This is the Higgs. The Higgs mechanism, the Higgs field. And this equation, which fits on the t-shirt, it tells how these particles interact with each other by exchanging these force bosons of particles. And the first 2 lines describe the force particles themselves. That's the first line. The second line is the interaction between the particles and the forces. And then, since about 1967, we've had the additional 2 lines here. It doubles the complexity of the equation, which is how the Higgs field interacts with all the particles which have a mass, and how it changes the nature of the weak force with respect to electromagnetism. It makes it extremely weak. So, I don't expect you to study this diagram, but this is just showing how all the particles can interact with each other through the force particles, and how some of the particles, like the W, can interact with itself and the gluon by itself, because they also carry the charge of the interaction which they couple to. And Higgs boson is the same. It carries a kind of charge and couples to mass charge, and many particles have mass. So you have Higgs boson there. The Higgs boson has mass, so it also couples to itself. This funny diagram here is not meant to be taken literally, but it's not completely idiotic to do that. But it shows how matter particles like the electron interact with quarks, for example, by exchanging a photon, a particle of light. And then these quarks, they get accelerated when they're produced, and they might radiate a gluon. And then out here we will have some other particles. This is Peter Higgs, one of Peter Higgs' 2 articles in 1964, where he's describing what he thought was the Higgs theory at that time, but there are other people working on the same mathematics of physics. So today we call it the Brout-Englert-Higgs mechanism, because there's another group of 2 guys who published within a few weeks of him. And there's an equation here, and there's a very important statement about the equation. This equation describes waves which want to have their mass. And these waves were waves of matter bosons. And before these papers, we didn't know how to give mass to the matter bosons in a mathematically consistent way. And this is what Higgs and Brout-Englert showed us how to do in such an equation. But this equation predicted more than how to give mass to other particles, it also said that, later in the article, about 2 pages later, it says that these formula predict additional particles called scalar bosons. This is what we call the Higgs boson together. So this is a vital test of the theory. It's not enough to find out that particles have masses and interact in some organized way, but we have to find this Higgs particle. And it wasn't until 2012 we found this particle at CERN. And the physics of this is that there's something in the vacuum, call it material. I've seen an article by a Nobel Prize winning physicist who calls it material in the vacuum, which gives mass to some fundamental particles, and it's been tested in experiment after experiment after experiment since the 1970s, confirming that theory, but only indirectly. So we have, until 2012, we hadn't seen this extra particle which comes in addition, which would confirm the theory. Now, I made a video explaining what is the Higgs particle in relation to the Higgs field and why it's important, but I'm not sure I dare to play it because the last time I did it, I crashed my laptop. But if you want to take a picture of this thing here, it will take you straight to the YouTube, but I can put it up again later. So this is the poor man's version of my film. Imagine you have a field of journalists. And this group of journalists represents the Higgs field, something in the vacuum. And then a famous person comes in the door. Here it's Albert Einstein, but in my film it's Justin Bieber. What happens? All these journalists, they want, the latest word. Why did you get arrested? What's your next album? Who's your girlfriend? And he tries to cross the room, but they cluster around him, and then there's kind of this big, massive thing crossing the room, not just one person. And this represents a very heavy particle. So this field has given a big mass to this particle. It started out without mass, now it has mass. What is the Higgs boson? It's an excitation of the field. Now someone comes to the door and shouts, Jens Stoltenberg or Angela Merkel is coming soon. They actually don't come. What happened? We lost the picture. We lost the picture. Okay, imagine this picture without Albert Einstein in the middle. So the journalists are now clumping around the rumor. They thought this politician was coming, and they wanted to talk to him, but there's no politician, it's just the rumor. And so this disturbance moving through the room of journalists represents the Higgs boson itself, and it's massive. Now, if a not-so-famous person comes in the room, like me, I can just go straight through the room, no one cares. I don't have any mass. So that represents photons, particles of light which have no mass. They are not disturbed by propagating through the vacuum. They can be produced at one side of the universe, and if they don't hit a planet or some dust or something, or some free electrons, they will arrive at Earth. Yes. I have another illustration of the Higgs boson. I saw this in Colorado last year. It's a bit more complicated. There are two kinds of photons. There are kinds which spin right-handed and spin left-handed. But there's no photons which do not spin. But what the Higgs boson does is it allows the W and Z, which mediate the weak force, to have a third kind of themselves when they don't spin. So that's represented by this slinky. So photons can go sort of back and forth. They can go up and down. These are two independent motions. Now, because there's some material here, there's a third mode of vibration, which is along the direction. So this kind of wave has no spin. And that represents both the Higgs boson itself, which has no spin, and this third kind of the W and Z bosons. And without this material in the vacuum, the W and Z would also be masses like the photon. The sun would burn up in an instant. The electron would have no mass, and we wouldn't have chemistry, biology, or life. So it's rather dramatic. So before the 4th of July 2012, this theory was very, very detailed and complete. It made very specific predictions. It told us almost everything we need to know about Higgs boson, except for two things. One, the obvious, whether the theory was right, and Higgs boson existed or not. And the other thing it didn't tell us was the mass of the Higgs boson. So when experimentalists went looking for it, they didn't know how heavy a particle to look for. So we've been looking for decades at higher and higher masses. And we need particle accelerators with more and more energy to make these heavy particles. And each time we go up in energy, we haven't found anything until 1.5 years ago. The situation can be compared to this. We have a picture of some young guys playing some kind of game on grass, two different uniforms, and they're all focused on a point up here. So we can guess what's up there, right? It's a football. And indeed, this picture came from a football game. You've probably heard about the God particle. So Leon Letterman, who wrote the book The God Particle, the name most physicists hate, he described this kind of analogy of the Higgs boson. We know more or less everything about it except whether it exists. However, it was not so obvious. There were plenty of people who thought the Higgs boson was a bunch of hooey, that it was just mathematical elegance. There was no connection to physical reality. And one of the creators of quantum mechanics, Werner Heisenberg, he told Brout-Englert, who was one of the 6 people publishing papers in the late 1964, he said, "You don't understand how physics works. Your theory is worthless." Stephen Hawking bet well-known Higgs hunter Gordon Kane, who belongs to the book called Higgs Hunter's Guide, which I've read, and all my students have read. He bet against the existence of the Higgs boson, and he lost $100. A lot of these stories. So we think we do what we're going to find, at least some of us. But it's very important to do these experiments, because what happens if instead of finding this, we go out and we check, do a reality check, and we instead find this? That's even more exciting. Okay, that didn't happen. There's a possibility. So CERN. This is the laboratory where I work, where the Higgs boson was discovered, where CERN is one of the founding member nations. It was where the World Wide Web was invented by now Sir Tim Berners-Lee. And why did he invent this thing? Well, I didn't know it until December. But he was going around asking the question, suppose CERN discovers an experiment, CERN discovers the Higgs boson. How in the world are all these physicists, because we have become big collaborations, in the 1990s the collaborations were 400 or 500 people spread all over the world. How are we going to work together to write an article when it's not going to take 3 years because you have to send it around through the snail mail and email and stuff? So that his hypertext transfer protocol on the World Wide Web was an answer to this question we're asking. That's also where it was discovered. This is an aerial view of the Geneva area. It's Lake Geneva. There's the Geneva airport. There's Mont Blanc in the background. This yellow thing is a drawing of where the tunnel is, 100 meters under the ground. It's about 27 kilometers around. The CERN laboratory is over here. Inside the tunnel is a bunch of superconducting magnets, among the world's strongest magnets, 27 kilometers on them, more or less. And they're very cold. They're kept colder than outer space. And inside the magnet is a vacuum pipe. And the vacuum in the pipe is better than the vacuum on the surface of the moon. It's a very special place. At several places around the ring, there are these shafts, and the experiments are built around the ring at places where counter-rotating beams of protons that go around both directions collide. experimental apparatus is called CMS. It's opposite, more or less the opposite side of it. So the APIS collaboration, in 2011, we had members from 38 countries spanning most of the globe. This is about 1/3 of the collaboration at a celebration dinner. This is the organization of the collaboration, which looks like a large business or a decent-sized university. These pages here, these are not articles. This is just a list of all the departments, institutes, and laboratories participating in the APIS experiment. This is the author list. The actual physics article, which came after all this, was like 6 pages. This seems crazy, but we would not manage to do these experiments if we didn't work together in these big groups. A small group of people could never do this work. This is about half of the group from Oslo, my group. We're preparing for the Holmenkollen relay race in May. There's a corresponding group at the University of Bergen, which we collaborate with on ATLAS. So what is ATLAS? I call it the world's largest digital camera. And it's partly made in Norway. It weighs 7,000 tons, so it's a bit heavier than your iPhone. It's about, which corresponds to 100 MP7 47s. It has 90 million pixels in 3D. Most of them are around the collision point, but there are many, many thousands all the way out. It's about 45 meters long and 22 meters in diameter. We keep, when it's running, the experiment's running, we keep 400 pictures a second. We throw away 20 million pictures a second. We take them, we decide very quickly if there's anything interesting, and if not, we throw them away. If there is, we're not very many, we keep them. And this gives us several thousand terabytes of data a year, some of which is stored and memorized in Norway. And then the second most inner part of the detector, we find these modules, which are related to the CMOS chips you have in your mobile phones for taking pictures. But they're detecting charged particles coming out from a collision. And they made something like 288 of these small modules about this big. So what is the challenge of finding the Higgs at the LHC? We're looking for about 10,000 Higgs bosons in 1,000,000,000 billion proton-proton collisions. And someone has compared this to looking for a needle in a haystack, but it's much, much more difficult. It's looking for hay in a haystack. In the sense that, okay, it turns out there are different kinds of hay, which is a help. But what we're looking for is a certain kind of event. Here are 2 particles of light, 2 photons. Here are 2 electrons and 2 muons, the heavier plus another electron. I don't have time to tell you how the detector is seen on this one. It's on the plan. But the point is that some place there could be a little accumulation of hay, some extra hay, and this will get us excited. But this alone was not enough to get us really excited, because the chances that this could happen by accident were pretty high. We have a little accumulation here, which again was exciting but not super exciting. And we have some extra data here, these black points above this blue, which is the background, it's kind of the other hay. But what we did is we combined the information, because the Higgs particle is expected to give all these other particles in the detector, and we combined them into a statistical analysis, and this was kind of my specialty, in order to ask the question, have we seen a Higgs boson or not, or is it inconclusive? Now, we didn't know the mass, as I said, but in early experiments we had eliminated masses below about 130 times the proton mass, we call it 110 gigaelectron volts. So we looked at all this region, and this black curve here, which is dancing up around 50%, if it shoots down somewhere, this is evidence that there are Higgs bosons being produced in our experiment. And if this is all we had seen, up here we would have said, there's no Higgs boson. But when we remove this curtain, here's the thing shooting down, and we have a kind of a threshold we set for ourselves. We call it 5 sigma. It corresponds to some probability of being fooled by
random data, and reached out all the way down to 6 sigma, which means that the chance of getting such a peak as this is 1 in 1,000 million, a billion. I call this, it looks a bit like a heartbeat, so I call this the heartbeat of Higgs. Our colleague competitor experiment CMS, they saw a similar heartbeat at the 5 sigma level at the same mass. This was really convincing. We both saw something which was super exciting. We saw it both at the same mass. This was amazing. And this is the Director General's reaction to the 2 presentations on the 4th of July 2012.
Okay, I can only say congratulations also to Atlas, of course. Should I say that I'm pleased? I think it's obvious. As a layman, I would now say, I think we do. You agree? Yeah.
I was lucky enough to be in the room at that historic moment. It was really exciting. It's like being in a rock concert. But we didn't dare to call it a Higgs boson because we had just barely seen it. And the Higgs boson has a lot of properties described by the theory, and we had barely scraped the surface. But we've taken 5 times as much data since then. We've analyzed the data carefully, and it looks just like a Higgs boson should. So this was a press release in March of last year. New results indicate part of the discovery is a Higgs boson. So now we say without reservation it is a Higgs boson. We knew it was something new. We weren't sure it was a Higgs boson. Now we're sure. And among other things, 2.5 times a day, we gave a much, much stronger heartbeat, plus all these other results. We gave something, we were at 6 sigma, and we went to 10 sigma, which is the probability of being fooled by random fluctuations in the data of 10 to the -23. This is comparable to building an LHC and an ATLAS experiment and a CMS experiment in every solar system in the universe, and only 10 of them would give a false discovery. It's really amazing. There's almost nothing in physics which is less uncertain. In May of last year, I gave a talk summarizing the discovery and the first measurements. The convener of the session I gave a talk is Fabio Gianotti. You may have seen her flash by on the cover of Time magazine, which has become a world celebrity. She was the number 5 person of the year in 2012. And my mission, given to my organizers, was to make sure the experimentalists get the share of the Nobel Prize. And if you follow the Nobel Prize in December, you know that I failed. So these 2 guys got the prize, Englert and Higgs, and this space here is what his collaborator, Robert Brout, who died 3 years ago. So why did they get the prize? They got the prize for the theoretical discovery of a mechanism that contributes to understanding the origin of the mass of particles, and was confirmed to the discovery of the predicted fundamental particle by ATLAS and CMS at CERN. So we feel like we did a really hard piece of work, and we only got an honorable mention. So my outreach officer at the department, she went and bought us some chocolate Nobel Prizes for consolation. It's not very unfortunate. It was very interesting because there was a press conference on the 8th of October. And usually these things go like clockwork. At 12 o'clock, they come out of the room, they sit down, they start reading. But now nothing happened at 12. At about 10 past 12, boom, came out and said, oh, we're very sorry, but there's been a delay. Be patient. We'll be out in about 10 minutes. And this happened 3 times, and the total delay was an hour. So we were asking ourselves, well, what's going on? Can't they find Peter Higgs? Because it's well known he's a very, very shy man, so he'd probably gone on the ground. Not to be called. Can't the committee make up their minds? There's another possibility. It turns out it was a second. And I think it was the first time in history, there came a leak from the Nobel Committee. Usually they're very, very good about keeping their secrets. All the documents are sealed, and they can only be opened something like 50 years later, and no one ever leaks anything. But some poor guy in the committee, he leaked. He got yelled at the next day by his boss. But he leaked that the committee couldn't make up their mind. And the fight was, how should we give something to the experiment like this, and how do we do that? So one possibility could have been to give it to the director of CERN, representing both experiments and the whole laboratory. And we would have been very happy about that. I mean, a lot of us working in the experiments expected to get it ourselves. We thought something about CERN should get it, not just the theorists. So now you're wondering, is that the end of the story? Is that the end of particle physics? It's the end of my research field? The answer is no, because there are a lot of unanswered questions. One which I'm working on is, are there more than one Higgs boson? We don't know. The theory doesn't set a limit on the number of Higgs bosons, and there are many theories saying it could be 5. So we have to keep looking. But probably the big question in particle physics and astrophysics and cosmology are the questions of dark matter and dark energy. So this satellite has measured the temperature of the universe in all directions in the sky. And this is a temperature map of the universe. And there are very, very small fluctuations, and they can interpret these. And their interpretation says that, okay, we understand about 5% of the material content of the universe. 5%, 1 out of 20. So there's an awful lot of stuff, which is a mixture of stuff which behaves like matter, but it doesn't react to light, it's dark. And an even bigger bunch, which is some dark energy, which is making the universe expand faster and faster. We have no idea what it is. So these are big questions. So another question is there some relationship between the Higgs field and the dark components of the universe? We don't know. We're doing research to find out. This is another experiment on a satellite on the International Space Station looking for antimatter in outer space. And it's not so easy to make antimatter and for it to survive. But if there are sources, nearby sources of antimatter, it could be dark matter particles colliding with each other. And this is an energy spectrum for anti-electrons. And it goes down. And if it goes down sharply somewhere, it will be very strong evidence for these dark matter particles. If it just kind of goes up and dies slowly, it will be evidence against it. So this is a big question for my viewers are interested in. So summary, on the 4th of July, 2 years ago now, we discovered a Higgs-like particle announced in the CERN. The results from additional data led us to call the new particle a Higgs boson, without a doubt. And these experimental results were the justification for the Nobel Prize in Physics in 2013. So one long era has ended, and we've gone into a new era. Now the Higgs is not the question mark anymore, but it's become a part of the zoo of particles, which we can build additional on. Thank you.
and calculate how much this piece of lead that I had weighed. Not by weighing it, but by knowing the atomic mass.
Yes.
And this interest have stuck since then. And I learned that inside this nucleus there are protons and neutrons. They are consist of smaller things, like we said, quarks and other particles. But then I heard about quantum field theory, and that got me really excited. There are not really particles at all, but actually fields, like the Higgs field, and everything is just fields. And these fields are interacting with each other, and that's why we experience the world that we are experiencing as mass. So it's not really a question, but just...
Well, I want to correct something, because yes, it's a field. The field is it's a mathematical function. And an electron has a field associated to it, but it's a quantum field. So the electron is quantized. It has a specific charge and a specific mass. You may not be able to pin down exactly where it is and how it's moving at some point, but it has a very specific existence. It's not some kind of a soup or water. It is somewhere, we just don't know where. But if you get a collection of electrons together and study their properties, then they can behave like waves. So if you send a beam of electrons into a crystal, like the two-slit experiment, but now not light is sending electrons into a crystal, the electrons will interfere with each other just like water waves. That if the water waves cross like this, some places you get double peaks, and some places they'll cancel each other out, pass through each other. The electrons will behave just like that. So they're both particles and waves.
That brought me onto the first question I wrote to my mail. Was you said that these fields are mathematical equations.
Yes.
But that's a way to look at them. And there's an aesthetic sense what guides the research.
Yes.
So what I heard.
So we are obsessed by symmetry and small deviations from symmetry.
What do you mean by symmetry?
I mean, there are many different kinds of symmetry, but one kind of symmetry is translational symmetry. That if we do an experiment where we collide some marbles against each other, and then we do the same experiment 1 meter to the left, the results should come out the same. They don't depend on where the experiment is done. If we do the experiment today, or in 5 minutes, or 2 years, if all the other conditions are the same, we should get the same results. So that's a symmetry or invariance with respect to time. So now the standard model equation which I flashed up there is a very special kind of what we call phase symmetry or phase invariance. So in the wave equations, if we twiddle the phase of the electron field at every point in space independently, a little bit randomly, the only way to get the equations to work and be self-consistent is to postulate there must be another term, which is an FU beginning, which is the photon field. And what that's saying is that in order for these electrons to have a phase which we can't see experimentally, then it must be hidden from us by some symmetry principle, and this symmetry is propagated through the photon, through light. This is one of the most beautiful, in essence, of the word theories we know about. We predict how forces work by postulating a symmetry principle.
How are the equation extended?
There's not much to look at, but it's what they predict. And the predictive power they have, which is pleasing. If you have a theory which only predicts one thing, it's worthless. But if you make a theory to predict the lowest energy level of hydrogen, and the same equation says, well, there must be higher energy levels of hydrogen that can just decide it somehow. And then you go and you do the experiment. Find these energy levels in the experiment, different colors of light coming out of heated hydrogen atoms, but very exciting. This is very beautiful. This is the Bohr model of the atom.
And that's what happened with the discovery of the Higgs particle. It was hinted that in another, or in an equation that something else.
Actually, the story is very complicated. When Higgs, Brout, and these other three guys worked in the 60s, they were trying to solve problems in strong interactions. And we didn't know anything about quarks and gluons back then. So we knew about protons and neutrons, and the lighter particles called pions and glow mesons. And we had no theory to give masses to these other hadrons. So they were wondering if this mechanism could be used to explain the masses of some of the hadrons in this big thick book. Well, today we know that the masses of the hadrons are given by the masses of the quarks and what kind of quantum mechanical state they are, that the hadrons have an internal structure, which we didn't know about in the 60s. So we don't need the Higgs to give mass to the proton. It's enough to have the quarks bound together by gluons in a stable state. And the energy which binds the moving quarks together gives the proton neutron mass. But in 1967, Steven Weinberg, he thought about a different problem, and that is that people were trying to understand the relationship between the weak interactions, radioactivity and hydrogen, and the electromagnetic interactions. They were trying to make a model of exchanging bosons. So there was a proposal for W and Z bosons, but it was mathematically not consistent because there were only two kinds of photon. And if we had only two kinds of these other particles, they would be massless, and the interaction would be too strong. It would not be a weak interaction. So Weinberg said, what if we recycle this Higgs mechanism and apply it to a weak interaction? I just introduce a couple more terms in the equation, and wow, now I can get the mass of the electron, and the mass of the W and the Z, make the weak interaction weak, make the Z and the photon particle mix to give some surprising behavior, which we later confirmed in many experiments. So this was the birth of what we call the Standard Model. And the Standard Model from 1967 has always included the Higgs mechanism. It has been with us for 50 years.
The Standard Model, that describes all the particles with mass, and the particles that carry
mediate the forces.
the forces. And the forces are the gravity that are not understood.
Yeah, okay. So the standard model incorporates three. I could have made a longer list of mysteries. The standard model incorporates three of the known fundamental forces. And the fourth, which is the weakest of all, is gravity. And we don't have a good quantum field theory description of gravity. We have Einstein's general relativity, which tells that the presence of energy could be energy in the form of light, or it could be energy in the form of mass, like the mass of the Earth, distorts the space around it. You get a potential well, and things want to fall into that well. And so we stay planted here on the surface of the Earth because we want to fall down, but the Earth is holding us up. And that force is not unified, we say, with the standard model.
But in the standard model, there's the electromagnetic force that we know well, and we use it in the computer, for example, the light. And there's the strong force that binds the neutrons together, and the weak force that has something to do with the radioactivity. I have a question. What is the difference between energy, force, and charge?
Okay. So, force is an influence on something, an object, a particle, a system, and it can change the system, it can change the system shape, it can give it energy, it can break it. In the microscopic world, the force is the exchange of a particle changing the direction and maybe the identification of another particle. This is a force on a very fundamental level. But on a more macroscopic level, it's an influence which has some measurable effect. Often it results in changing motion or energy. Energy is a kind of it describes the state of a system, and there are different forms of energy. One form of energy is potential energy, the potential to exert some movement later. Like when I pull on my slinky and then stop, I put potential energy into the spring. There's a force there which I'm working against. And then if I let the spring do work, so the energy which was potentially in the spring, it goes into movement in my hand. Like the force to energy. Charge in the particle world is something carried by many of the particles, which determines how strongly these exchange bosons grab onto them, couple to them, we say. So the bigger the charge, the bigger the probability to have interaction. And even some of the force particles also carry the charge in their own interactions, so it's mathematically quite complicated. So charge is not energy, it's a feature of the particle or object which allows work to be done or to change its energy.
And that brings me on to the difference between weight and mass. And then we have gravity. because energy and mass isn't just two different things.
Well, they're two sides of the same thing. You've probably all seen Einstein's famous equation, E equals mc squared, saying that the energy of a particle which is at rest, if it has a mass, is not zero. It has some inherent energy, which is its mass times v1c squared. So like the Higgs boson has a mass of 125 gigaelectron volts. So in principle, if we captured one of them, it could decay to 120, well, let's say half protons and half antiprotons, all at rest. It wouldn't happen, it's very improbable, but it has enough energy stored in its mass to do that. And this mass distorts space. And that distortion of space is what gives us gravity, that things are pulled to some point, like towards the center of the Earth. And the weight is the force you need to prevent the massive object from being accelerated in the gravitational field. So my weight is actually about 80 kilograms times some constant g, which is 10 meters per second squared. And that force, which is 800 newtons, is needed to keep me still here on the surface of the Earth. So if someone puts something under me and exerts a bigger force, then I'll fly up. And if you remove the floor from me, I'll go shooting down faster and faster.
Can you say a little more about the particle wave relativity? Is it a conceptual thing, or is it?
There are conferences, a number of conferences every year where the experts get together and they discuss this kind of thing. And there's no common agreement. So
It's a mystery that
it's a mystery, but we have the equations of quantum mechanics and we can apply them. And so far they've never been wrong. Sometimes they've been surprising when we understand and we haven't really formulated the right question. But like I showed you the pictures of, I don't know how to get that picture here. These pictures, these lines in the detector, a particle has gone through the detector and left little bits of energy, and this energy has ionized some gas, and then an electric field has pulled these electrons out of the gas and then let it out with some electronics. So these are electronic signals. And the tracks are curved because they're in a magnetic field. And so this particle has a very specific momentum, and a very specific direction. It comes out, goes there, it hits the rest of the detector and makes some other signals. So it behaves like a particle. If I want to calculate the probability of getting that particle with that energy in that direction in many, many collisions, then I have to use a wave equation to do the calculation. I cannot calculate with kind of Marvel equations. It's relativistic quantum mechanics, which are wave equations.
And the accelerator, you described how it's working.
Yes.
And maybe you can do that again.
Okay.
You start off with two protons going in opposite directions.
Well, let's say we have two circulating in the ring with some energy. They are circulating because there's a magnetic field which bends them in a circle. The magnetic field is pointing in one direction for the photons go this direction, and there's a separate vacuum pipe for the photons going like this with the field in the other direction. And they're both they go around in opposite directions, and then these two tubes, they cross in about 8 places. And 4 of these places, there are big experiments. Now, to get them up to that energy, we use radio waves. So we shoot radio waves into a tube where the electric field points along the direction of the vacuum pipe. And then we time the arrival of the protons with the side of the radio wave, and then it's almost like a surfer. It rides the wave through this radio frequency cavity and picks up energy the whole way. When the cavity stops, then the particle shoots off with a constant energy. And it goes around many, many times, and each time it picks up a bit more energy until we get the energy we want, and then we stop.
I was picturing the, like when you have a wave that don't interfere, but meets up at the same, the same at the top.
Yeah.
Fuse into one way, but it's not like that. It's a particle.
Well, we don't.
There you have a.
We don't really. I'm not sure how much we learn by discussing whether it's a particle or whether it's a wave. If we use wave equations to calculate the probability of how many particles we will see at some point in our detector, and we do the whole calculation of waves, we get the right number. Always.
And to get the protons in there, sounds very easy in a way.
Yeah, we go to a local gas manufacturer and we buy a bottle of hydrogen gas. We plug it onto the end of the accelerator complex, and start off with an electric field which rips the electrons away from the nucleus, which is a proton, and then they escape into the next region where there's a field which accelerates the protons off in some direction. Let's see a question back here.
Yeah, so first of all, thanks a lot for a really interesting talk for someone who's complete layman in these things. So I'm going to ask you a real layman's question. I can't ask the kinds of questions that Daniel has investigated. So I understand that one of the amazing things about the discovery is this totally beautiful formula which is totally symmetric, and predictability that has never existed with any other kind of experiment. Like you were describing this with, if you did the same experiment in all over the universe, that's an amazing kind of predictability that we so far haven't yet experienced in any other kind of experiment. So if I understand you correctly, that's part of what's really special about it. Maybe, I'm sure maybe you can correct me here. But basically you describe this as a new era that has arrived. So I wonder, could you say, is there a way for a layman to understand what this new era looks like? What is different in the new era?
Yeah.
Because that is a really big statement, and I'm really curious about what the new era might look like to a layman.
So let me try the first question first. So we have other theories which make predictions which have been tested to amazing precisions. And one of those theories is the quantum theory of the electron, quantum electrodynamics, which is a low energy theory. And I forget how many decimal places it's tested to, but it's flabbergasting. It's much more than it is. What was special about getting another half years of data was how significant the observation was. So not that it was predictable, but that it could not be a fluctuation of the data. This curve here is that we could get such a bump just by random fluctuations, and they all happen, whoop, to happen in this nice bell-shaped curve in some place. But when we saw this here, and this here, this one is not so clear, but it also contributes, and this mass are exactly the same, and we have an additional experiment seeing the same thing. Oh, the probability for all these things happening together is just astronomically small. It became even smaller with the new data. So now today we could discover the Higgs boson just with this data here. Okay, this is not the full data set. This is only the July. So the full data set, if I showed you, would be even more impressive. These little black uncertainty bars would have shrunk a lot. And there's no way to get that randomness. And the second thing, why is it the new era? Many years ago, when the theory of electromagnetism was being developed, Maxwell understood that electromagnetic waves they propagated light waves. People were asking, well, they must be propagating in something, because we know about sound waves. They go through air and water and the table. And we know about water waves, and you can make other kinds of waves. So the light must be propagating in something. And this something was called the ether. And so they thought, okay, the ether is what the light is propagating in. But I'm not sure if Maxwell was saying himself that we don't need the ether, but experimentalists looked for the ether. A famous experiment done by two guys, Michelson and Morley, proved that there is no ether. The light can go through vacuum. It doesn't need to shake anything. It's just the light itself which can continue. But now this Higgs theory is, in a way, taking a step back. It's saying, oh, wait a minute. Okay, so the light waves can propagate through vacuum, but these W and Z particles, they're not allowed to propagate. They are stopped. They're given an absolutely enormous mass. And what is doing that? And why are they different than the photon? Because it's the same kind of theory describing the photon as the W and the Z. And Higgs and these guys said, well, they didn't say it directly, they needed help of Weinberg. But these guys, they said, well, maybe there is something in the vacuum. And this something is changing the properties of some of the particles, but not the photon. And now we've shown that this vacuum material actually exists. And this is very surprising. And, we've kind of had our suspicions for a long time, but now we know it. The vacuum is not empty. We don't know how it got there. We don't know if someone put it there for us. But we know it's there.
Might be a absurd question, but could you potentially use Higgs boson for something? Except research?
This is a common question, and my answer is I don't know.
No.
I doubt it in my lifetime. But people were saying the same thing about the electron. When Thomson was discovering the electron, they said, what are you doing research on the electron for? I mean, it's so small, you can't even see it. It's useless. And he gave a talk at some party, and he gave a toast, here's to the useless electron. And now we make so much use of the electron. We couldn't almost imagine living without it, without mobile telephones, computers, electric heating, pacemakers, microwave ovens. I mean, the list goes on and on and on. And okay, I don't see how to use the Higgs field in some practical application, but who knows? I do know that if we don't find out these things, they will never be used. And the motivation doing these crazy experiments with all these people and then collaborating forced someone to think about making something like the World Wide Web. It wasn't some government saying, oh, please go make the World Wide Web for us. We want to change society. It was some guy working in the science lab saying, oh, these guys, they really, the way they work together stinks. they need to get organized. We have this network, let's try to use the network to help them in their work. Now, okay, you can always find bad uses of the internet, but also very many good ones.
Is there some relationship between the Higgs boson and black holes?
We don't know, because if you calculate the energy density in the Higgs field, it's wild. It's like orders of magnitude different from what we need to explain things like dark energy or any properties of the universe on a large scale, galaxies, clusters of galaxies. We don't know so much about black holes. In fact, I just read a week ago that Hawking has made a new kind of interpretation of black holes. He says black holes don't exist. I don't exactly know what he means by that, but at least the simple-minded picture we have of a place where things and information just disappear into it and then never come up and are gone is not correct, he says. So it's a quite deep question you're asking. I don't think anyone knows the answer.
Are you sometimes concerned that it may have some negative consequences? What you find out, like
Yes.
the atom bomb?
Yes, but fortunately, we've understood enough to be able to predict things like that in advance and maybe take some means to make sure they don't get used in the same way that the splitting of the atoms used to make atom bombs. So I don't see any danger. Most could be wrong. But splitting the atom has also good applications as well. It might be a big part of the answer to the world's energy needs in the next 100 years. It does not look like we're going to be able to use solar energy and water energy to meet our energy needs. Either we need to drastically reduce the population of the Earth, or we need to learn how to harness nuclear power in a safe, clean way.
Do you think it's ever going to be possible
To
get this energy, atomic energy, in a safe and clean way?
It will never be completely safe, but what is? If you compare the number of people hurt by radiation to the number of people hurt by oil spills and natural gas explosions and poison and this and that, yes, it's scary because you don't see it. But the effects are the same. Misery and death. It's not done safely.
I don't know if you described it, but I remember you described shortly how the different particles, how they behave or how they interact, but how are they described? I mean, what are they made of, or like what's their properties? How do you define them?
This table is sort of the beginning, and all the quarks in this row have an electric charge of 2/3. The quarks in this row have an electric charge of -1/3. So if you put one of these and one of these together, you get a hadron of charge +1, like the proton. If you put 3 of these together, if you put 2 of these and 1 of these together, you get a proton, etc. As you go to the right, the masses of these particles increases. These are all fermions, so they have spin 1/2, which doesn't mean much to you, but it defines their property under electromagnetism very precisely. These guys have charge -1. These have no electric charge. They have almost no mass. For a long time we thought they had 0 mass. Turns out they have a very tiny mass. These have larger and larger masses off to the right. These also have spin 1/2. All these force carriers here, they have a spin of 1. The most important thing about having a spin of 1 is if they're not massless, you can have 3 states. Spin up, down, and in the middle. And if it's massless, you can only have the up and down spin. Then, as far as we know, this electron, well, we used to think that this electron number was somehow absolute. But now today we know these neutrinos can mix. So an electron neutrino coming from the sun can change into a muon neutrino or a tau neutrino by the time it gets to the Earth. Probability is not very high, but it happens. This is studied now both in underground experiments, measuring cosmic neutrinos, neutrinos from the sun, neutrinos from nuclear reactors, and then particle physics experiments. We have a beam of particles and then a neutrino detector far away. What else? So these heavier quarks here, they have properties which are related to the names charm, strange, top and bottom. And they're conserved under strong interactions and electromagnetic interactions, but under weak interactions, you can get transitions from one generation to the next. Then there's something called the parity, which is how the interaction works if you look at it in a mirror. Is it the same or does it get changed? Interactions with photons and muons, they have this mirror symmetry. But weak interactions violate parity maximally. So the interaction looks very different if you study it as a mirror image. And in fact, it's going a bit astray, but from this table and the properties of these particles, we can communicate with the rest of the universe that we are made of matter and not antimatter. Because it turns out there's a very small difference between the properties of matter and the properties of an antimatter universe. And we can send some formulas or some pictorial diagrams to another part of the universe and say, we are made of matter, what are you made of? Well, if they receive something in the form of matter, of course it would explode on contact. But if it was a message, they could answer back what if they were matter or antimatter. But actually we believe that the whole universe is made of matter because we don't see any place in the universe where matter and antimatter are meeting and making photons, which we can see on the images. So that these particles have a lot of properties and described also in this big book. But they're not all stable, so some of them have what we call a lifetime. They have some probability of decaying to lighter particles. The top quark decays in 10 to the minus 23 seconds. So it's so fast, you can't believe it. The charm quark is called charm because it has it's charm, so it has a long lifetime. And the strange was called strange because they were very easy to make in cosmic rays, but they decayed very slowly. And that was strange, because if they're easy to make, they should also decay quickly. So there's a long list of particle properties which are precisely tabulated. Yes?
You said that the vacuum in space is not empty, and then if there is any place that is actually empty, such as inside the atoms between the electrons,
talked about the fields of the different particles. For most of the particles, the field of the particle in a vacuum is zero. The particle has kind of position somewhere, and everywhere else, there's nothing. The Higgs is special because it has what we call a vacuum expectation value, which means that the probability of there being a Higgs particle anywhere is not zero. You can't escape it. You can run, but you can't hide. Even inside the atom, away from the particles, there's the Higgs field. And it's changing the mass of the electron, which allows it to bind to the nucleus and make an atom. So as far as we know, there's a Higgs field everywhere. Well, people ask, well, why? Yeah, so there's this Higgs field and it's the same everywhere. What is keeping it the same everywhere? So there's a crazy, half-crazy guy in this course in Copenhagen. He says what is stabilizing the Higgs field is a vacuum explosion a long time in the future. So it's a very crazy theory. But he has some mathematical explanation how a vacuum explosion in the future is giving us, it's almost like a temperature which is the same everywhere in the universe. It's like a goldfish in a tank of water. And it goes around with a thermometer and says, wow, that's curious. Everywhere here in the tank, the water is 0 degrees. Why? Why isn't it a bit higher, a bit lower? And he looks down and says, oh, it's because there's a big ice cube and some air. And if you have, at the right pressure, if you have a presence of ice and water and air or water vapor, it keeps the same temperature. If the energy of the system is right to the beginning. So this vacuum explosion in the future is supposed to be like the block of ice, kind of making sure that the temperature can't change. If you try to melt the ice, you get water at 0 degrees. The ice tries to freeze the water, you get ice at 0 degrees, etc.
Talking about crazy ideas and theories, what are new things that are working on CERN?
Well, one is we're looking for Brout-Englert directly in CMS. And we have a theory which fixes some small problems with the Higgs theory at very, very high energies, and allows us to make a unified theory. In fact, some versions of the theory can also include gravity. It's called supersymmetry. And like the Higgs theory, it makes some specific predictions and some not so specific. So one of the things is that for every particle, there should be a new supersymmetric particle with a different spin. There shouldn't be one Higgs boson, there should be 5. It doesn't tell us anything about the masses of these particles. So whenever we get stuck, we have to go and start checking at 0 mass and then work our way up. And right now we're up to about 1 tera electron volt, roughly. And we haven't seen any sign of this supersymmetric particles. But from next year, we're going to double the energy of the LHC. We're going to run it at twice higher intensity. So there's still some hope to see signs of supersymmetry. And one of the supersymmetric particles is a very good candidate for this dark matter, which doesn't react with light, but is heavy. So it reacts with gravity and affects the form of the universe, affects this temperature map I'll show you. Questions? I'll hold it down.
I read somewhere that soon there will be quantum computers. Is there a possibility to use these particles to make something like a computer?
No, this is unbelievably unstable stuff. It's just disappearing.
So not reverse.
And for a quantum computer, I mean, you don't want it to kind of disappear on you, right? You have to use some heavy calculations to at least live for some minutes. So they're typically using atoms and very, very cold systems, not very high energy. This is very high energy physics, and these things are more like super, super cold things.
But they will not become quantum computers.
People are working on them, and some of the people working on them are optimistic, others are not so optimistic. So the proof will be what the experiments are able to demonstrate. It's difficult. It's difficult work.
Yeah. I read somewhere that some scientists proposed that because when you do these calculations, there's always some limits and stuff, that it's actually more probable than not that the universe is a simulation or something like this. Did you read this?
No, but this is getting off into, I don't know, philosophy or metaphysics or something. It's also a problem for cosmology because they only have one experiment, the universe we see. My research is much easier because I have to be able to prove it can be done again and again and again. It's reproducible. It's a kind of different kind of science. So we don't know if we're going to test whether the universe is actually a simulation of someone else's computer at the time.
I think you said something about the universe is expanding faster because of dark energy,
Dark energy.
Yeah. Like, why?
I mean, dark energy may turn out to be like the Higgs, that we can actually show that it's a real effect, or it may just be a lack of understanding. Because we're starting with Einstein's general relativity, and then he has a free parameter in his theory, which is not determined by the theory itself. And if you set that parameter, it's negative, then you get this kind of force which has no physical interpretation, pushing things out. And maybe we'll actually do some observations which help us to understand. Maybe there isn't an expansion. Maybe we're being fooled by some other effects which we're not thinking about. Because the measuring the redshift of light made by atomic transitions in galaxies, and when we look at them, the nice line we get from our hydrogen lamp, it's coming at the wrong place. It's not coming at the same place we see here on the Earth. It's coming at the lower energy, longer wavelength. So it's the so-called Doppler effect. Who knows? Maybe there's something else besides the Higgs field out there, which is slowly reducing the energy depending on the distance. I don't know. But we don't know what dark energy is. We have a mathematical description of it, but we have no physical interpretation. There's nothing in my experiments which can say anything about dark energy. So I don't think we're going to see. I think the first progress we'll see is identifying dark matter, and already that will get us up to 30% of the universe extent.
I know you're not an artist, or I guess most of the people here come from art or a civil background. So just curious how you think art or aesthetics can contribute to knowledge. Or yeah, I mean, how can it contribute to knowledge?
I don't know. I mean, like we talked about, we have this kind of aesthetic appreciation of some of our equations and the theories. They're not so pretty to look at written out on a piece of paper, but they have some kind of beauty, and symmetry is an important concept, and contrast. I don't know. There's a program at CERN, if you would be interested. It's only 1 or 2 years old, where there is some kind of fellowship, and artists propose some kind of project, and then they're invited to CERN and they're supported. They go around and try to get some kind of impression about what's going on and how people think, and what is the meaning of knowledge, and then to represent this in a play or painting or a sculpture or whatever. So if you go to the public CERN pages, search for art, you'll probably find this art scholarship page. But I don't know. I mean, we don't spend a lot of our time thinking about how artistic values can influence our research. But you know, we're people and we process information which we get visually and audibly, and some of us spend some thought on how we present our results to try to make them intuitive, to get some feeling to them. I didn't get to show it, but I introduced a kind of style of showing results which people call Brazil plots now. And any particle physicist, when he sees one of these, she sees one of these plots, they know exactly what it means. And that was the closest I come to artistic contributions and color scheme way of making it.
I'm just going to, I know there's other questions. I always get the feeling with art that when it tries to interpret or collaborate with technology or specialists from another field, it really struggles to deal with the content. So I'll just, that was my...
I mean, the comment about my field, you know, I showed you these event displays, but the astrophysicists and cosmologists, they beat us because they have these beautiful pictures of the cosmos, of galaxies, of threads of black holes, of dark matter, very, very visual. Our event displays are kind of the best we can do. It's, straight lines, curved lines, what's the big deal? It's not very exciting. So you next, I think?
I wonder, are there some religious people in this group, or who have religious motives for this search?
I haven't met any, but there are certainly religious people doing particle physics, not because they're religious, and they haven't gone into particle physics because they're religious, but they're just there. And, you know, it's part of their worldview, and it's okay. You may have noticed in the media, we have a nun in my research group, Ms. Catalina. And she has no complex about doing research in particle physics and being a nun, devoting her life to love. I don't know of any sort of real fanatics. Of course, there are plenty of fanatics that read stuff and then try to make something out of it, like quantum theory, whatever. But we don't find them at our laboratories and physics departments. So you look like a lot of that.
Yeah, I mean, now the few really interesting thoughts have come up, one of which relates to religion, I think, is that, of course, your research asks us to constantly question everything we ever believed in or everything we thought we knew about. And that's why I guess the question of religion comes in, like, if you're religious, no matter what religion is, maybe the research will lead to you having to abandon belief in God or God, it's like this and like that. That's just a thought. But and another thought is that, well, there's a writer I think I very much admire. He's called Brout-Englert-Higgs. Some of you might have heard of him before. And he's done a lot of reading in your field, but he's a philosopher, and he's compared it to some Sufi Islam theories and philosophies that he's analyzed from medieval times. So there are also religious aspects of some religions that actually correspond to the new kind of research you're doing, or so he claims. But anyway, that was not my question, that just came up now. My question was a bit more related to what you were saying. There's a saying, the limits of our world are, or the other way around, the limits of our imagination are the limits of our world. And maybe artists can stretch the limits of our imagination, but I wonder, like, since you say a lot of the things we ask these layman questions, the researchers don't have the answers to those. And is that really because all of us don't have the necessary imagination? We just cannot imagine things, and a way to go beyond the limits of our imagination are the mathematical equations and the experimental exercises you're doing. I'm wondering what you think about that.
I mean, there's I would call it a thriving industry of ambitious young theorists. And they need to get a job. So they're postdoctoral researchers, they finish their PhD, they want a permanent position, so they're trying all crazy things. So they're stretching in every direction and dimension and trying to find something new. And, you know, a lot of it is probably junk. But these ideas, they don't come with little flags saying this is the right idea. For instance, Weinberg's paper in 1967, I think, if I remember right, in the first 3 years he got 2 citations. This is a paper which today has like, I mean, it's 6,000, which is, in science, it's a huge number. It didn't take off until some other people showed some additional good mathematical properties in that theory in 1971, I think. And then suddenly, whoop, everyone understood that that paper should have had a flag on it in 1967. But for him, it was just another paper. Oh, this could work, that could work. Here's a model. But now it's a standard model. They've had it for over 20 years. So maybe out there, somewhere, even now, there's a paper which is taking us to the next level of understanding the universe, but we just don't know which one it is. It's not easy.
I know what you said in the book, but are there any hypotheses or idea on what dark matter is?
Well, as I said, there's a very good candidate for dark matter in this theory of supersymmetry. And one of the candidates is called a neutralino. And a neutralino is a mixture of, it's kind of a mixed particle, it has lots of properties. It's a mixture of Higgs, is picture of Higgs and photon and Z-like particle with a different spin. And it has quite a big mass, but it doesn't interact with light, with photons. And it's stable, so it doesn't decay. So they're just kind of floating around and then being kind of attracted wherever there's gravity. In fact, they're self-attracted because they're heavy. So I've seen a simulation of the galaxy structure of the universe where they painted in where they think there could be strands of dark matter. It could be these particles from this theory of supersymmetry. But if this theory is right, we ought to find these particles in our particle accelerator experiments in the next 3 or 4 years. There are also underground experiments looking for evidence of dark matter particles coming, and they almost never react, but once in a while they can react with some detector in the signal. These two ways of looking for these dark matter particles are complementary. There are other kinds of dark matter candidates, but they're somewhat less likely. There used to be something called machos, massive, compact halo objects. This was like, I don't know, kind of planet-like things which are dark, give off their own light, they're cold, and there are a lot of them, but we don't see evidence of that. So we don't really hear about them anymore. But the most popular thing is RIM. So the macho is RIM, like weakly interacting massive particle. That's one of the things from this supersymmetry. So we don't know the answer, but we have some ideas what to look for.
Maybe one last question.
Any other questions? Answered?
I think so. I think we didn't touch on it. I would be easy.
Yeah, I want to come back to something you said, because maybe I said it already. Yes, I did say it. The mass of a proton and a neutron, our mass is not due directly to the Higgs boson. 99% of our mass is due to the binding energy of the quarks inside the protons and neutrons.
So what mass is?
But without the Higgs field, the electrons would be massless, and they would not bind to the protons. We would never have hydrogen, and then we could never start to make stuff.
Does that mean there is a set number of Higgs bosons in the universe?
No, I don't think so.
So it could be random, or it changes, or...
Yes, it's random. It's not set.
I think we'll have to